Let's be honest, we are drowning in data. It's everywhere. News headlines, ads, social media posts. And look, statistics can be an amazing tool for understanding our world. But that exact same power can be twisted to mislead, to manipulate, and sometimes to just straight up lie. So in this explainer, we're going to arm you with the tools you need to spot those lies before they can fool you.
This quote, right here, just absolutely nails the core problem. Are the numbers being used for illumination, to actually help us understand something new, or are they just being used for support, to prop up an argument that someone's already decided is true? That right there, that's the crucial difference we need to learn to spot.
Okay, so how do you tell the difference? Well, that's exactly what we're here for. We're going to break down the most common statistical tricks of the trade and give you a simple toolkit to see right through them.
Let's start with that central idea. Using data for illumination means you're genuinely curious. You're open to whatever the numbers tell you. But using it for support? That means you've already made up your mind and you're just hunting for a statistic to back you up. We're here to learn how to seek that light.
All right, let's dive into the first, and maybe the most common trick in the book, creating the perfect picture. This is all about manipulating what you see and how you see it to paint a version of reality that, well, isn't real at all.
This one has a name you've probably heard before, cherry picking. Imagine this. A school district rolls out a new curriculum, and they want to prove it's a massive success. So they publish a report showing amazing test scores, but only from their top-performing schools. They just conveniently leave out all the schools where the curriculum bombed. By picking only the best cherries, they've created a totally false narrative. Cherry picking is one thing. It's about hiding the data you don't like. But what if you show all the data and just present it in a deceptive way? That's where misleading visuals come into play, and frankly, they can be even more powerful. Take a look at this. At first glance, product B is the clear winner, right? I mean, the bar is like twice as tall. The difference looks huge. But the trick here isn't the data, it's the graph. Look really closely at that vertical axis on the left. See that? It doesn't start at 0. By chopping off the bottom of the graph, the creator is visually blowing a tiny difference way out of proportion. Now let's see that same exact data, but with the axis scaled correctly, starting from 0, where it should. All of a sudden, poof, that giant gap basically disappears. The difference between the two products is revealed for what it really is. Tiny, maybe even insignificant. See how that works? Without changing a single number, they made a molehill look like a mountain. Okay, our next trick is a little more subtle. It preys on our love for that very official-sounding phrase, statistically significant. It's a trap that lets people find what look like meaningful patterns in what is actually just complete random noise. This is called data dredging, or you might hear it called p-hacking. It's what happens when someone doesn't start with a clear question. Instead, they just run test after test after test on their data until, by pure random chance, they find a connection that looks significant. It's not science. It's like throwing 1,000 darts at a wall and then drawing a bullseye around wherever one of them happened to land. There's a famous saying in statistics that sums this up perfectly. If you torture the data long enough, it will confess to anything. And that is the heart of the problem. If you test enough random things against each other, you are guaranteed to find a correlation eventually. The only catch? It's almost certainly meaningless. And for a perfect and kind of ridiculous example of this, get this. A data analyst actually found a statistically significant correlation between the number of letters in the winning word of a spelling bee and the number of people who died from venomous spider bites. Obviously, one doesn't cause the other. This is exactly what happens when you just dredge for patterns. You find them, even when they're totally absurd. And this isn't just some funny academic exercise. A journalist once pulled off a brilliant hoax by creating a fake study that proved eating chocolate helps you lose weight. He used p-hacking on a tiny group of people, tested a ton of variables, and found a random correlation. The scary part? Tons of major news outlets fell for it, hook, line, and sinker.
All right, get ready for this next one because it is a true brain twister. We're talking about a phenomenon where the data seems to clearly say one thing, but when you zoom in and break it down, it says the complete and total opposite. It's called Simpson's paradox. It's when a trend shows up in different individual groups, but the second you combine them all together, that trend completely flips on its head. I know, it sounds impossible, so let's just walk through a real example to see it in action.
So here's a study comparing two treatments for kidney stones. Now look closely. For patients with small stones, treatment A is better, right? 93% success versus 87. Okay, now look at patients with large stones. Again, treatment A is better, 73% success versus 69. So it's a no-brainer. Treatment A is the better choice, period.
Wrong. Now look what happens when we combine all the patients into one big group. All of a sudden, treatment B looks more effective overall, 83% success compared to A's 78%. Wait, what? How is this possible? Treatment A was better for both small and large stones, but it's worse overall? That is the Amson paradox. So what happened? The answer is a hidden factor, what statisticians call a lurking variable. In this case, it was the size of the stones. Doctors tended to give the better but more invasive treatment A to the most difficult cases, the patients with large stones, and they gave the less effective treatment B to the easier cases, the patients with small stones. So treatment B's overall success rate looks better simply because it was used on way more easy-to-treat patients. Wild, right?
Okay, so we've seen the tricks, the cherry picking, the misleading graphs, the peacocking, the mind-bending paradoxes. Now for the most important part. How do you actually protect yourself? Let's build your very own Data Skeptics Toolkit. Your toolkit really comes down to 4 simple questions you should always ask. First, what was the original question? Was this an honest investigation, or were they just fishing for a headline? Second, demand context. Could there be a lurking variable, like with the kidney stones, that's flipping the results? Third, scrutinize the visuals. Always, always check those axes. And finally, number 4, ask yourself what you're not being shown. Is it possible that this is a classic case of cherry picking, where all the inconvenient data got left on the cutting room floor?
Ultimately, knowing these tricks isn't just about being cynical. It's about being a responsible citizen. When we demand transparency and ask these simple questions, we all help build a culture where data is used honestly, as a tool for real, effective change. So, the next time a shocking statistic or a dramatic chart flashes across your screen, you'll be ready. You'll know how to ask the right questions. You'll be able to decide for yourself, are you being handed a lamppost just for support or a light for true illumination?